Today's my lecture topic is solid rocket propulsion. The basic solid rocket propulsion consists of the solid rocket motor. The solid rocket propulsion solid propellant rocket is formed by four main components: a case containing the solid propellant and withstanding internal pressure when the rocket is operating. The solid propellant charge, that is grain, which is usually bonded to the inner wall of the case and occupies before ignition the greater part of its volume. When burning, the solid propulsion is transformed into hot combustion products. The volume occupied by the combustion products is called combustion chamber. The nozzle channels the discharge of the combustion products and because of its shape accelerates them to supersonic velocity. Next one is the igniter, which can be the pyrotechnic device or a small rocket. Starts the rocket operating when an electrical signal is received. One can consider that the solid propellant after manufacturing is in a metastable state. It can remain inert when stored, or it can support after ignition its continuous transformation into hot combustion products. The velocity of the transformation front is called burning rate. The solid rocket is therefore inherently simple and therefore can possess high intrinsic reliability. After ignition, a solid rocket motor normally operates in accordance with a preset thrust program until all the propellant is consumed. All the effort should be directed to the accurate prediction of the thrust programs to get the benefit of a solid rocket motor concept. A solid rocket motor has a variable internal geometry related to the continuous transformation of the solid propellant to combustion products. Change of the combustion area in time will result in change of pressure and thrust. A steady state view of operation can be adopted by considering different geometries separated by an increment of displacement of the combustion surface. An elementary analysis can justify this approach. The main issues of solid propellant rocket motor are: development of a solid rocket motor requires considerable technological investments in different domains. These investments are substantial given the severe conditions inside the motor: high pressure around 5 megapascal or 50 bar in the larger boosters, high temperature around 3500 Kelvin for a composite material propellant, two-phase flow material propellant. The critical technologies concern the propellant itself, the propellant grain design, the thermal insulation, the nozzle design, and the case. Besides, another well-known difficulty is related to the near impossibility to perform detailed measurement inside the combustion chamber due to the severe conditions prevailing there. The only useful measurement is the static pressure measurement through a pressure tube, generally at the motor front end. This difficulty can be considered as one of the main obstacles to the perfect validation of the prediction tools. As this short course is devoted to the aerodynamics, attention will now focus on a particular topics. Burning rate. Propellant burning rate plays a central role in major operation. That is why perfect control of burning rate is absolutely mandatory. Fundamentals and recent development regarding burning rate will be developed in another lecture. The discussion will here limited to steady state regimes. Normal regime burning rate is depending on only two parameters: pressure and initial temperature. It is known that burning rate can change with the propellant temperature, since only a very thin layer of the propellant is usually affected by the chemical transformation during the combustion process. A good assumption is that the initial grain temperature is an external parameter without variation during operation. Sensitivity to pressure is related to the chemical reactions in gaseous space above the combustion surface. Some parameters are defined to characterize local propellant, and it should be mentioned that the pressure component should be lower than for a practical one.